Okay, so thank you for introduction. So today, I'd like to talk mainly about our motivation and challenges that we address in our paper, and technical details. I don't have enough time to talk about technical details. So the topic of this paper is CHC solving. It is a problem to find a solution of a set of constraints involving a predicate variables, and the problem to find an appropriate assignment to predicate variables. And there are examples of CHCs. And the first example is satisfiable. That means there exists a solution for P. It is easy to check that this is actually a solution. And the second one is unsatisfiable. It is a relative, it may not be obvious, but it's actually unsatisfiable. So because CHC solving has many and wide applications, many efficient CHC solvers have been developed, especially in this decade, in the last decade. And in this talk, I exclusively focus on so-called acyclic CHCs, but I do not introduce this notion formally. But one important point or justification of this focus is given like this. The acyclic CHC solving is actually a key ingredient of modern CHC solvers. And another important property is that this is decidable under a mild condition on the background theory. And let me explain the behavior of modern CHC solvers by using example. And this is an example of CHC. And this graph is an illustration of the constraint and dependency between predicates. For example, an edge from here to here, P0 to P1, means that there exists a constraint which has P1 on the left-hand side of the arrow and which has P0 on the right hand of the arrow. So this means that this constraint. Okay. And GPDR maintains some kind of over-approximation for each predicate variable, and which is almost a solution, but does not meet exactly one constraint. And GPDR tries to strengthen this assignment so that it finally satisfies this last condition as well. And in order to do that, it propagates the information of the points that should not be included in each predicate. For example, here is a direct constraint on P0, meaning that P0 must be false on 0. Okay? So we propagate this information. We express this information like this. So we have to strengthen P0 so that this should be satisfied. And this kind of information can be propagated by backward. And given this kind of request, GPDR tries to resolve it locally first. That means it tries to change the assignment to P0 without touching assignment to any other variables. And we check if it's possible in this case. In this case, it's impossible because P0 is true on -1, and this condition together with this first constraint forces that P0 must be true on 0. So, So we know that, we now observe that P1 must be false on -1 in order to achieve this goal on P0. So we propagate this information to this predicate. Then we try to resolve this locally, and it's possible simply by letting P0 to be x not equals -1. And this does not contradict any other constraint. So we can update it. So we do that. Then we now have a new assignment to P1, and we again check if P0 and this request can be resolved locally. And again, it's impossible because P0 is true on -2, and this fact together with the first rule forces that P0 must be true on 0. So we propagate this information, and this can be resolved locally like this. So we do that. And then for this new assignment, we again go back to the period P0 and check if this is resolved. This can be resolved locally, and it's impossible. So we propagate this like that. And you may notice that this process may diverge. And this is a possible diverging scenario of GPDR. And this is unfortunate because acyclic CHE solving is decidable. So there exists a terminating procedure that solves this problem. So this divergence behavior can be avoided, at least in theory. And actually, there exists a very natural and simple terminating solver if we are allowed to use quantifier elimination. The point is that the divergence, the reason of the divergence in the previous scenario is that the back image of this point along with this arrow has infinitely many points. So removing points one by one does not terminate in general. So the idea here is to use a set of points instead of a point. And fortunately, in this case, we can describe the precise back image by using quantifiers like this. So this says that this is true if x is in the back image of this along with this line. So then we can resolve this locally like this. And in this new assignment, one can resolve this request for P0 locally like this. And we have done. And this is terminating sound and complete solver. So this is good. But there is a weak point. That is, this requires quantifier elimination that is usually very, very expensive. So we would like to avoid use of quantifier elimination. A technique to avoid quantifier elimination is known as model-based projection. And it is not easy to explain this in detail, but intuitively, it cuts the QE formula into a finite number of pieces, and it returns one piece of them by using additional informational model. Let me explain this by using example. Let phi be this formula, then exist x, exist y, phi is equivalent to this formula. Then a possible option, possible MVP is defined like this. It returns this component or this component depending on the value of the model x on, the model m on the variable x. And what is interesting is that MVP has an efficient implementation. Despite that, QE is very expensive. And the characteristic feature of spacer is a extensive use of MVP. So intuitively, this kind of quantified formula is replaced by MVP. And because MVP is more efficient than quantified elimination, the procedure is more efficient than the naive procedure using MVP, quantifier elimination. And in this case, fortunately, spacer is terminating. But this is actually limited to linear CHCs to the best of our knowledge. Okay. So spacer is proposed as a procedure for solving non-linear CHCs. So I'd like to explain a more complicated situation. A CHC is nonlinear if the left-hand side of arrow may contain more than one predicate variable. And in this case, spacer behaves like this. Now, assume that we would like to strengthen R so that it meets alpha. In this case, assume furthermore that this cannot be resolved locally. Then we have to strengthen either P or Q. In this case, spacer tries to strengthen one. First, tries to strengthen only one of them by calculating a sufficient condition for example, Q, such that this request can be resolved locally without touching P at all. And this is a quantified formula. So we want to check if this is true on Q, or this can be satisfied by Q. But quantified formula is expensive, so we apply MVP. Okay. So we obtain like this. Okay. And this procedure looks very reasonable and fine and natural. But unfortunately, there exists a diverging scenario. This is an example. The point here is that the left-hand side of arrow contains two predicate variables named P. So it has two occurrences of the same predicate variable. Okay. So let's assume that this is the first assignment, and then we would like to force Q to be bottom. And we check if this can be resolved locally, and it's impossible because of the first rule together with this assignment. Okay. Then, then we need to strengthen P. So we would like to we generate a request by using MVP, and this is one of the possible return value of MVP. Okay. This does not generate at all. So we request this, and this constraint can be resolved locally. So we do that. Now the situation is like this. We updated assignment to predicate P, and then tries to resolve this locally, but it's impossible because of the first rule with this assignment. Okay. So we apply MVP to generate a new request for P, and in this case, it may not generate at all. So we request that, and locally resolve that, and so on. And we can continue to do that. So this procedure look diverge, and it is actually possible scenario for spacer. If you are familiar with MVP, you may wonder why the finiteness insurance of MVP does not help to terminate this situation. This is because we apply MVP to infinitely different formulas, but the finiteness guarantee of MVP is ensured only if it is applied to the same formula. So this scenario actually occurs if one chooses very bad MVP. And what is surprising is that this diverging scenario does not seem to have been found but that does seem to be overlooked for a decade. And this suggests that reasoning about MVP is quite hard. So we think that we need some structure that makes it easy to reason about. And our aim is to develop a procedure that is defined by structural induction and use this inductive structure to reason about the procedure. To achieve this aim, we developed first a procedure that is correct and terminating, but inefficient using quantifier elimination. And then we tried to make this procedure efficient by rewriting it, basically replacing quantifier elimination by an iteration of model-based projection and the application of MVP as lazy as possible. Okay, so I plan to explain the basic procedure using quantifier elimination, but unfortunately I do not have enough time to explain the detail of the procedure. So please see the paper if you are interested in. Then our paper also includes some more detailed argument on how to modify this procedure by using MVP in order to obtain a terminating spacer-like procedure, as well as a new procedure with more sophisticated control flow using coroutine this is some kind of continuation mechanism. We also compare our proposal with many variations of spaces, and we implement our proposals and do evaluation on using CHC benchmark set. Yeah, and this is a cactus plot. Yeah, and this is a conclusion. Thank you for listening.
So we have time for a few questions. So in the meantime, so what class of CHC theories are amenable for this reasoning? For example, like let's say a particular CHC theory does not have quantifier elimination.
So you, for theories without quantifier elimination, the problem is very, very undecidable. So there is no hope to obtain terminating procedure, but this idea itself is applicable. And actually, the same happens for spacers. There is a variant of spacer over an undecidable theory. And there is an empirical evaluation that works well. So we expect that.
So there is some work in the space of spacer that extends it to LIA plus arrays, right?
Right, yeah.
So does your work can be applied to that domain?
Yeah. To obtain a procedure, of course, but it's not terminating in any sense, or no refutation complete.
Yeah. Hello, thanks for a nice talk. So I was wondering, you started by explaining going over spaces through GPDR.
Okay.
I was wondering if your approach could be generalized for other solving algorithms that are not IC3 or PDR based, like transition power abstraction and other solving engines.
Yeah, that's a very interesting question. Transition abstraction. So that's very interesting, but we haven't yet tried to explain that kind of technique in our framework.
Thank you.
Thank you.
Any more questions? Let's thank the speaker.